I'm here to talk to you guys about bloated chefs. I hope ChefConf has gone okay for you so far, and almost over, promise. So today we're talking about bloated chefs, which really kind of is just chef client optimization. Some patterns that we put in and how those patterns have scaled over time as our infrastructure grows, and the problems that we've seen as a result, and how we went about fixing those problems. So first I'll tell you a little bit about me. My name is Evan Gilman. I'm an ops engineer at PagerDuty, and was previously a network engineer at the University of Miami for several years doing routing and protocol analysis and things like that. So today, just a quick agenda. What we'll go through, first we're going to start off with some chef resources that are in use at PagerDuty, some resources we wrote to give you kind of some context around what we're going to see. Some problems that we encountered as we grew the infrastructure with those resources and these patterns that we put in place. How we went about measuring the chef client run statistics to kind of determine where these problems are and how best to attack them. How we actually fixed those problems and the impact it had on the run as a result. So obviously we're a chef shop, quite large chef shop. We use Chef to manage all configs of all different kinds. We use it also to do kind of a search-based service discovery type mechanism. We also use it sometimes to coordinate cluster-wide operations, things like scaling database clusters, things like spacing crons out around rings, and stuff along those lines. But really, I think we use it most heavily to control the network and network automation, and also configure third-party services for us, things like configuring alerts and setting log sources and stuff like that. So as I mentioned, we're going to go over a couple of the chef resources that we use inside of PagerDuty and what they're all used for, and it'll hopefully kind of flesh out some of the context later on in the deck here. So the first provider that we wrote was PDIP tables. PDIP tables is basically a role-based rule generator, and allows us to control the IP tables rules in kind of chef land. So it works by creating role chains of roles, right? So each chain is named after a particular role, and the chain contains all the hosts that have that particular role applied to them in the infrastructure. And then this LWRP just drops IP tables rules that have jumps to those particular chains. So we can do port admission based on chef role, which is pretty cool. We also use it to control all of our IPsec automation. So at PagerDuty, we use IPsec, peer-to-peer full mesh IPsec, which means that when any host communicates to any other host, it communicates over IPsec. And in order to do that, we have to drop a policy for every possible relationship in the infrastructure. So this is what we're doing here. We do a search for all the hosts in the infra on the chef server. We enumerate all of them, we each over all of them, and we create the relationships and rewrite them to disk using the template. So this is a good example of an API-backed LWRP that we wrote. It's obvious, it's pretty self-explanatory. We use sumo logic to do all of our log indexing and search. And when we want to configure a source for sumo logic to scrape from logs, we have to do it with an API call. They don't allow the client to be configured for sources. So this basically just declares a source to be indexed by sumo logic and makes an API call to see if it's already configured, and if not, it sets it. And the last one is also PD Datadog Alert, which does a similar function. It's also API-backed. And we use it to create alerts in Datadog for particular stats D thresholds. The first instantiation of this LWRP will fetch all of the alerts that we have configured in Datadog, and we'll use that data to kind of check again, do the idempotency checks. So it's kind of large in that way. But you can see that most of the uglies have been abstracted. So the interface of the LWRP is quite terse. It's easy to use. It's easy to remember. When you have something like that, they kind of become like fun to use. When you write them, it kind of gives you some joy that it's so simple and easy to understand. So these are just a few of the resources that we've written at PagerDuty internally. We have all these shiny, really nice, fun to use resources that we clobber together in all kinds of interesting ways. So you feel pretty good about it, you know? You feel like you can conquer the world, right? But in reality, all is not well. there are major, major problems with some of these patterns as we figured out. So as we grew, we began seeing some shit. So the frequency and severity of these problems would continue to increase as the infrastructure grew. The first problem we saw was just basically CPU spikes during the chef runs. Chef runs would occur, and CPU would go crazy, and we could even sometimes see this effect on the application and the application statistics. That the chef run is starving the application for CPU time. The next problem we saw were these really, really weird pauses at the beginning of the chef run. Chef run would start, it would output some stuff, and then it would be silent, sit there silent for a while. And sometimes it would sit there so long silently that you're like, I don't even know if it's still running or not. Maybe it's hung or something. Then, we kind of woke up and realized that our chef client run times were just completely out of control. Some of them exceeding 3 minutes. It would take us well over 30 minutes to converge the entire fleet, sometimes approaching an hour at the worst of times. And finally, the final nail on our side kind of was chef client just began moving. and sometimes the exception would be thrown by the problem resource or cookbook, but not always. So sometimes it was a little more difficult to kind of track down where the issues were being introduced. Here's a screenshot of our hip chat room. It's supposed to be red, but screenshot of our hip chat room showing one of the out-of-memory errors on our chef run. Seeing this pop up is super depressing. Let me tell you that. You see this thing and you're like, oh man, you can't even get chef to run. So you finally wake up, you've gotten into this spot where chef is so slow, you can't roll stuff out fast enough. You can't even reliably converge the whole fleet at once. So all these errors and problems are coming up, failures left, right, and center, and it kind of induces this really weird claustrophobic feeling, like I'm being trapped, like I've all this weight on top of me. You can't move. So, you used to kind of feel like this dude here. But after a while, you really kind of feel more like this guy. The weight is coming down, you can't go anywhere. It's awful feeling. So, how do we fix it? It has to be fixed. Obviously, the first thing you got to do in order to fix something is start measuring stuff. So we set out to try and find ways how we can measure chef client run and all the various things that are within it. We know we have problems with both memory and CPU because we're affecting the application and we're seeing OOMs on the chef client runs. So we have to collect metrics on both of these things during the run. The way we accomplish most of this stuff is using a chef handler. One open source chef handler and one chef handler that we wrote internally. And the handler that we wrote stores a bunch of statistics on the node object as attributes. So when you do one run, you can send a change and then do another run and kind of compare the data points and see, okay, did we use more or less memory on this run than the last? The handlers will also emit statsd, can be configured to emit statsd. So all of this data we're collecting can also be kind of visualized over time and see how we've done in the cleanup and things along those lines. So here's a good example of that. This is a graph of our chef run time over the past year, all the work we've done on it. So this is some of the data that our handler captures and omits as statsd.
That's seconds on the...
Seconds, yes. So this is great. It's super cool. And it's great for measuring overall progress, like how have we done in the whole optimization, scheme. Though it doesn't really help immediately because you already know your chef client runs are taking a long time. You need to know what in them is taking a long time. So an even better way to measure this is by resource or cookbook. So there's an open source chef handler called Chef Handler Profiler that we use to do this. Measured both cookbook and resource time spent in each one. And you can see in this list actually is quite dominated by resources that are actually making API calls. So those that tend to take longer than anything else we're doing in the run. Our custom handler that we wrote also can measure resources bucketed by type. So we can see how many resources of a particular type were declared. We can also see how many of those resources were actually updated. This is super useful for identifying non-idempotent resources, resources that have problems in the idempotency checks, which will definitely slow down your run, and those can become rampant. So this is very useful in identifying which resources were having these kinds of issues. We also had to measure the memory. So we used a sysproc table gem to measure proc data, which basically just exposes it as a hash, which is real nice. One of our engineers found that gem. So we used the sysproc table gem to scrape proc data about the process ID that Chef is running under. And along that proc data comes memory consumption statistics. We also gather GC stats, kind of understand how GC is occurring over the course of the run. And as I mentioned before, all of this stuff can be emitted with stats-D, and so you can track this stuff over time, which is super convenient. This is just a quick screenshot of some of the node attributes that we set with the GC statistics. So we got all these measurements. We got some data now. What did we find about that stuff, and how did we fix it? So the first problem that we noticed was the searches were awful. Major problems with the searches. So we had several searches returning all nodes in the infrastructure. The IPsec tooling and the IP tables tooling in particular required a search that would return all nodes in order to fully populate the topology files that we're trying to generate. As the infrastructure grows, so did the volume of node data. So these searches just kind of grew and grew and grew. They consume a lot of memory by the end of the day. So we found that you can actually pass the chef search method a block. Rather than taking all the nodes into a variable and then eaching over the variable, you can just patch it the block you would have eached over anyways and allow it to do that. So you kind of page through the nodes as opposed to loading them all up at once. So this is the old search we had. You see the search on the top there. We take all the node data in, and then we just each over it and perform what we have to perform. So we go from a pattern like this, something like this. So you pass the block directly into search, yes?
So does that cut down on memory and time, or just memory?
So that cut down on just memory, yeah. I'll show you in one moment exactly how much. So we pass the block up to the search directly, and that way, as I said, you can kind of page through things as opposed to taking this huge blob of all your node data and doing these operations on it. So you ask, what the impact is, and it turns out the impact's quite a good bit. It saves a lot of memory, and especially saves a lot of memory if you're doing this pattern in more than one place, which we were. So changing it to use the search block, we went from 417 megabytes on a chef run to 190 megabytes on a chef run, which is about 54% after only touching a few of these searches. So that's pretty good. It's respectable, certainly, but it's still 190 megabytes. So we think we can do a little bit better than that. So now we don't have to store all the node data in memory at once, but we still have to page through it and process it, and we still have to download it from the Chef server, and certainly there's a lot of other things that are still causing a problem here. So the answer to that is partial searches. Many of you may already be familiar with partial searches. But basically what it is, it allows you the search to return only the data that you're trying to get off of that node object. It's pretty easy to use. You just pass it a hash map of the attributes you're interested in, and then it returns a hash map containing all the values of the attributes you're interested in. The best part is that the amount of node data returned and processed is dramatically reduced. So, sweet. That's what we're looking for. There's only one problem, though. It returns a hash map, not a node object. Searches usually return node object. So many methods, especially methods that we write in-house, often take node object as an argument to kind of compute differences between nodes and things like this. So you can't just drop the partial search in. So we still need the node objects. So the answer to that was hash to node. We wrote a method called hash to node that basically takes a hash as input, constructs a blank node object, and shoves all the attribute data into the node object, and then returns the node object. So now we can actually take that data from the partial search, create a proper, partially created node attribute out of it, and pass it to whatever helper methods we need. Yes?
Really specific to your environment. The fact that you need a node object.
So the question is that it's specific to our environment, and in particular, the methods that we've written take node objects, but I know that also some of the internal chef methods also take node objects. So it's entirely possible that other people are encountering this as well. I mean, if not, then great, but I'm not a big fan of the difference where partial search returns a hash and regular search returns a node object. So even outside of that, I think hash to node is still valuable because you can kind of make that consistent across the different methods. So we solved that problem for us with hash to node, which was good. We like that a lot. So now that problem's solved, we can actually switch to partials on a couple of our most painful searches. And the improvement was immediately obvious, like glaringly obvious. So our runtimes before this change were averaging about 90 seconds or so. But after this change, 60 seconds. So 30% reduction from only changing these two searches in our infrastructure to a partial search. The funniest part about this actually is that most of this time wasted was time in gzip, because the Chef client was uncompressing all the node data that had been sent to it by the server. And so this would occur at compile time. So that really weird, awkward pause at the beginning where you think that Chef is hung, all this data, search data, is being consumed and iterated upon. So you can imagine 30 seconds of Chef not outputting anything at the very beginning. It's like, what's going on, It was really, really weird. So we got that gone, and that was great. So now we're really kind of feeling like we're getting somewhere with this thing, So the next target we wanted to do is minimization. So you kind of want to cut down on these computational efficiencies in our runs. We do a lot of searches and things like this that are expensive to generate, and it makes a lot of sense for us to store those results for use later on in the run. Search data is the big one. If we need all the node data, grab it only once. Store it, use it in other recipes, right? So again, the IP tables and IPsec automation in particular, both of these need all node data. And it doesn't make sense to do it twice, especially when the volume is very large. And it's not uncommon for us to have the same search happen more than once in a particular run, because one recipe will need it and another recipe might be needed as well. Another thing that's pretty high on this list is API-backed LWRPs. So you notice in the previous slide where I showed the resource runtimes, all the ones at the top are API-backed. Session initiation can take some time, more time than you might think. Grabbing the data you need to do the item potency checks may take some time, more time than you think. A good example is our Datadog LWRP that I showed. In order to do its item potency check, if the alert's already created or not, we have to fetch all the Datadog alerts from Datadog, and then look at the data at the alert collection and determine whether it's defined yet or not, and if it's changed. And we have a lot of alerts, coincidentally. The good news is you can kind of generalize some of this memoization. So especially written memoization methods can store all this stuff centrally. So here's a super simple example of how you might accomplish that. So you can memorize. So here's an example of a method where you can memorize all the search terms in one method. And this is a shared library. So you can take this and you can use it in any one of the cookbooks or recipes that you have in your run and benefit from not having to do these searches again. You can also do this with, API clients, things like that. And it gives a nice boost to API calls, except the API thing is still a little bit shaky. It takes a while to do. You've got it in your chef run. Maybe it's in the base role. It's happening everywhere, right? 1 or 2 seconds might not seem like a lot, but times how many hundreds of hosts or thousands of hosts do you have? And they can slow you down, big time. So as the fleet grows, we found some interesting things. We're making all these API calls. And they become slower and slower until eventually the service that you're calling against just throttles you. And when you receive this weird 4xx response, a lot of times the client will just throw an exception and error out, which really sucks because then it's like, I can't converge all this stuff fast enough because we're being throttled, and then the Chef client runs are failing. So we're tired of the Chef run failure, so we added retries. But in reality, I mean, retries only make the problem worse, because now we're waiting 60 seconds on some API to quit throttling us instead of just failing the run and trying again. So in reality, I think the answer here is that we should just centralize all the API calls. A single service on a box somewhere, which consumes metadata from Chef and runs on cron or whatever, and then just validates that all the third-party services are accurate. What this buys you is your runs are now free of all these crazy dependencies, right? If GitHub is down or whatever this other thing is down, your Chef run's not going to fail. You're still going to succeed, and at some point in time when the API recovers, the job will pick up and be posted. It also frees you of all the unnecessary failures and things along those lines. So along the way, there are a few other nasties that we kind of discovered. Yeah. One of them was too many conditional guards. So we had a lot of not if and only if guards. Some of those would call binaries to do the check. And some of those binaries take a second or two to fire, especially if you're using Bundler. Because Bundler is notoriously slow to set up its environment and do all this other stuff. So if you have anything like this and not if checks, they contribute a lot to Chef run slowdown. And they add up quite quickly. If you have to use it only if or not if, use it, but just kind of keep it real simple as you can. Ruby is best. TempFS storage is another big one for us. We used a lot of TempFS storage for like remote file resources. So a remote file resource would download a tarball, store it on /10, and then would untard or something and install it. And then who cares about it anymore? Right? So you'd think, oh, just put it in /10. That's where it's supposed to be. The super common pattern for downloading and installing and compiling software. But the problem with this is TempFS. As soon as the box reboots, the file's gone, and a remote resource goes and downloads it again. So the Chef client runtimes after a reboot suffer totally when following this kind of pattern. So we went and we excised it all, and we use the Chef cache instead now. New with Chef 12, the package resource can accept an argument, a hash as an argument for which packages to install, or array. Sorry, not hash. Which is super cool because now when you have a recipe that installs a bunch of packages in your base roll, you can roll all those up into one resource. So you don't have to call apt a million times. And that is like, okay, well, I mean, that's pretty sweet, but I mean, did it really like make a big difference? I mean, it makes some difference. So we updated our PD packages cookbook. We had 12 packages in there. We shaved 6 seconds off of our bootstrap time just by using this resource as an array instead of eaching over. And as a bonus, it's totally way more readable. You just pass it, instead of creating an array and then eaching over it, you can just pass it the array directly and not have to worry about any of this nonsense. So, all this spiel, you might be wondering, all right, well, how much did all this stuff really help? Right? I have those numbers, so here's how much it helped. Before we started our crusade, our rampage on optimizing all this crap, our Chef runs needed about 500 megs of memory. Today, we're down to 60. Feels a lot better, right? It feels good. 88% less memory. It's actually only 12% of the memory consumption that we used to be enjoying, which is pretty awesome. Really happy with that number. It could be lower, but it's a significant reduction. So what about the runtime? At our worst, we're seeing about 180 seconds average chef run. 3 minutes about. But with all the optimizations we were able to make, most of which, or a lot of which were in this presentation, we were able to shave that down to only 30 seconds. So from 3 minutes to 1/2 minute. 84% faster than it was previously. It feels really, really good to see improvements like this so large, you know. And it feels really, really good to be fast again, you know. After some time of dealing with these slow runs, the fastness is invigorating. And it kind of makes you feel like you're like free, like freedom, you know? So a lot of changes went into getting us this far. You know, but there were lots of big wins early on, especially in the searches and the minimization and things along those lines. Chef was also upgraded a few times along the way, you know, so there were certainly improvements there as well. The upgrades bring new features like the multi-package feature, which you can further leverage to shave these times down. Right? And so that's most of the things I have for you today. I hope that some of these patterns you can at least recognize and take home and speed up your Chef client runs as well, because it feels super good to do so. I'd highly recommend it. But that's all I've got for you today. So thanks for having me. And I'd like to know if there's any questions or anything like that.
Any questions? All right.
You mentioned at the beginning there were 2 handlers that you used, one from Joe Miller and one that you wrote at PagerDuty. Are you going to open source that one? Or can you say more about what the special one does?
Yeah, so we have not open sourced it, but I don't see any reason why we can't. There's no PagerDuty specific stuff. I will make sure that we open source it very shortly, and it will be on the PagerDuty repository. Basically what it does is it just reaches in and gathers some of these metrics, and then it sets them as node attributes, and then also shoves them into, we use Datadog, so it also shoves them into statsd of the Datadog, and then that's pretty much it. It's pretty simple, but we'll make sure to get it out there. Yeah, absolutely.
So I'm pretty new to Chef, but I was a little curious when you were talking about Chef caching. Why? Well, could you elaborate a little bit more on that, and also maybe compare it with some other common places people would use for storing binaries, like Artifactory? Yeah.
So I'm talking more like when you download those artifacts, whether they're stored on disk as you manipulate them. The Chef cache that I was referring to is set as a config variable, and I think it's like var chef cache or something like that as default. And we usually use that because it's a good place to store things. It's not going anywhere. People use Artifactory to store artifacts and pull it down and put them in the right spot, but also along the Chef run, you often have times where, for instance, we used to compile Nginx. And so that requires pulling down the tarball, untarring it, running the compile script, that kind of stuff. And following that pattern, a lot of times you'll see the remote file being stuck in /temp, so that's kind of where that came from. And a lot less kind of deploying artifacts for a particular application or something like that. Does that answer your question?
All right. Over here. 1 second. So did the version of Ruby ever come into play? Like, I know I've run into, so debugging Rails applications, that's always...
yeah, the version of Ruby did come into play, and we did upgrade our version of Ruby in the Chef repo.
Yeah.
Though, the impact was questionable. There was some impact, certainly, but it was not the impact we were hoping for, given some of the other... I think that the biggest hit that we got, or improvement that we saw from upgrading Ruby was in the specs. All the testing was much faster after that.
Yeah.
But the Chef client runs themselves weren't impacted as greatly as you might think they would have.
Did you tune any GC settings as part of that too?
I don't believe so. Actually, Doug did all the work on that. He's shaking his head no. So.
Yeah, you can get some decent. It depends. So, like in a Chef client run, it may not be that big a deal. It's like 60 megs, so it's not.
Yeah. Well, now it is.
Yeah, right. Well, so previously it probably would have been.
Yeah, definitely.
Yeah. Right on.
All right. Any more? All right. Well, thank you very much. Join us at 4 for the Awesome Chef Awards. Let's give it up for Evan.
Thank you, guys.